Okay, so uh, we we were dealing with this greedy algorithms, and we were discussing this minimizing the lateness problem. Okay, and in the last class we have seen several templates we attempted, but only the earliest deadline is giving some hope. Okay, that okay. If we schedule the jobs with earliest deadline first, that means whichever job having earliest deadline or whichever assignment having earliest deadline, I should be trying to perform that assignment first. Okay. So here this we have to sort the jobs in earliest deadline first. Okay. And you see this first t will be initialized to 0. T will be initialized to 0. Okay. Nothing has happened yet. And then each job I am considering for j equal to 1 to n. Each job I am considering. And then we have to assign job j. We have to assign job j to interval t and t plus tj. Tj is the processing time of that job. Tj is the processing time of that job. Processing time that we have seen. Right. So tj is the processing time. That what is the meaning of this processing time that we have seen in the last lecture. And this t will be initialized to this sj, and then fj, that means the finish time, will be t plus tj. So if this job is starting somewhere down here, then after t plus tj time, that means after processing time of tj, that job will be finished. Okay, so that will be the fj. And then after processing, so this t should be incremented to this t plus tj, so that next job can start from this. Okay, and then we have to return these all these intervals we have scheduled. So this in the last class we had the example, last to last. So this is actually the example we are having, right? So earliest deadline first algorithm. So you see this DJ, this all these jobs are already sorted by the deadline. Okay. So yes. So the 6, then 8, then 9, then 9, then 14, then 15. Okay. With this order, we have to consider the job here. Okay. And this 6 is processing time 3, 8 is processing time 2, 9 is processing time 1, 9 is processing time 4, then this 14 is 3, 15 is 2. So with that we have to proceed. So this D1 is, that means the deadline with deadline 6, that is the D1 job, that is processed fast. Okay. And we have seen that T1 having processing time 3, okay, maybe 3 days. So you are starting your assignment first with this deadline first algorithm, and by 3 days you are completing. Okay. But you are having deadline 6. So according to our definition of lateness, we are not lagging behind. We are within the deadline. So no lateness here. And then the next job, whose deadline is 8, is being considered. And t is now incremented with t plus tj with the processing time. So it will be starting from here, right? And then its processing time t2 perhaps was 2. Okay. So this 3 to 5 it will be taking. So within 5 days you are completing, but the deadline of D2 was 8. So you are within time. You are on time. Okay. And then the next job is being considered, whose deadline is 9. And you see it's taking 1 day of time. T3 was 1, I guess. So it is T is again updated with T plus Tj. So T is now 5, 5 to 6, and the deadline is 9. So we are within time. And then D4 is 9, and its processing time perhaps was 4, I guess. T4 was 4. So this 6 to 10 it will be taking, and you see the deadline was 9, and here we are having 1 day late. Okay, so lateness is 1, and D5 is after that D5 is taken, right? And then this 10 to 13, it's 3 processing time, but we are within the deadline. And then the next job is taken up, and we are to 2 days it will be taking to complete, say, and then we are within the deadline again. So the maximum lateness we are observing is the 1. Okay. So 1 is the maximum lateness here. And if we run any other algorithm, that will not be performing better than this. Okay. So this is the earliest deadline first algorithm. Now we have to prove that, okay, this algorithm exhibiting this, if I'm going by this earliest deadline first, then we have to prove that this is optimal. Okay, this is optimal. So this proof is there, as I have already proved too. I am not proving this. I am giving this as an exercise to you. Exercise. Okay, right. I am giving it as an exercise. If at some point of time I am taking one tutorial class, then I can get back to this. Okay. But if I am not, you should be studying in your own that how to prove that this deadline first algorithm will be leading to the optimal solution. Okay. So this is for this scheduling problem. Okay. Three different types of scheduling we have seen, and now we can go to another important problem that is called the knapsack problem. Okay. So let me open that. Okay. So which one? Okay, I guess this one, maybe the knapsack one. Yes. Okay. Okay. So this is from this CLRS book again, right? So as in the previous slide was from the SKT book, and this is from CLRS again. So this is the knapsack problem. So we are discussing the 0-1 knapsack. What is the problem? Then we can discuss what is the fractional knapsack. Okay. So I'll be discussing this fractional knapsack today. Fractional knapsack. So let us see what this problem is all about, right? And this is having many different applications, the knapsack problem. So this is a very important problem for computer science, right? So the 0-1 knapsack problem is the following. A thief, a thief is there. He has entered. A thief is there, okay, and he has entered to your house, okay, with a big smile, right? Because you are having lots of items in your house. Say you are having n items, right? N items you are having, and with a big smile he has entered in your house, and in this ith item is worth VI dollars and weighs WI pounds. Okay, so there are several items you are having in your house, several items you are having, right? And this each item, say its total valuation is say $120. Okay, and its weight is it weighs WI pounds. Okay. So its weight is say maybe 10 kg. Okay. So this is each of these ith item having some valuation, that is VI dollars, and its total weight is also given WI pounds. And another item maybe $60, and it is with 15 kg. Okay. Another item maybe $100 with say 25 kg. Okay. So these are the items there. Okay. And the thief wants to take as valuable a load as possible. As valuable a load as possible. Let me check whether I'm recording. Yes, I'm recording. Mhm. Okay. The thief wants to take as valuable a load as possible. That means the items he will be taking in his bag. Bag is knapsack. Knapsack is another name is the bag. Okay. So you are having a bag, that is the knapsack, right? So that's why it's a knapsack problem. But he is having a constraint. Okay. But he can carry at most W pounds in his knapsack. His bag is not having unlimited capacity. As you see, whenever you are having a bag, you are carrying a bag. Okay, so whenever he is carrying a bag, right? So it should be having some limited capacity. Okay? Some limited capacity, and he has to take all these items in this knapsack. Okay, in this knapsack, and the total weight the bag can carry is this W pounds, right? Is this W pounds, and this W is for some integer W. Okay. So now this which items? The question is which items should it take to maximize the valuation of the load. Okay. So as valuable a load as possible you have to take. That is the main idea of this problem. Okay. So you are having n items, 1, 2, 3 here, n equals to 3 here in our example. And each item having a valuation and how much weight it is carrying, it is mentioned. Okay. And the thief has to figure out which items should he take so that he can carry as valuable a load as possible. Okay. So this is we call this problem the 01 knapsack problem, because for each item the thief must either will be taking that item or will not will be leaving it behind. Okay, will be leaving it behind. So that's why it is 01. That means either it can take or, just a minute, So either it can take it or leave it behind. So that means always it will be considering the case that, okay, whether what is the capacity, remaining capacity of my bag, and based on that he has to decide that either say the bag having say already he has captured in the bag say 10 and then 20, say 20 pounds and 10 pounds, and the bag remaining capacity is 30, remaining capacity is 30, okay, say, or say 20 remaining capacity, and he is the next item is weighing 40, okay, 40 kg. So even if his knapsack is remaining vacant with 20 kg in capacity, he can take, but he cannot take this item, okay, he cannot take this item to 40, because if he takes that item, his bag might, will not be tolerating that capacity, okay. So at that time 20 plus 10 plus 40 will be the capacity he has taken all, he will be taking already, but the total capacity of the bag is 20 plus 10 plus 20, so 50. So you cannot, he cannot, so he cannot accommodate this 40 here, okay. So he cannot accommodate 40. So that is the main bottleneck here, right? So this is the 01 knapsack. This is the 01 knapsack, right? This is 01 knapsack. That means either knapsack. So this is 01 knapsack. That means you can take that item or you have to leave it behind, right? That means if it is crossing the limit of the bag.